Okay, you know, on assignment 6, I guess we're calling this 6A, the exponential one, and 6B is the log one. So, these are the answers, the graphs. I'll go ahead and go through them. But you're supposed to answer increasing, decreasing, concave up or down, range, asymptotes, equations, composite. If you need to, check them. The darkened one is your final answer. You should have previous versions. And in the backside, these are the answers. So you can pause it. If you haven't checked your answers yet, hopefully you have. Okay, so go ahead and go over these. Okay, let's see. So these first ones are just graphs. So parent functions. This is just exponential. Really just looking for you to label that y-intercept and the horizontal asymptote, and then the graph looks like that, and that's your final answer. I mean, yeah, the bigger the base, the steeper the graph gets, but not looking for that. So this is increasing concave up. Range is 0 to positive infinity. The asymptote is y equals 0. So there you go. Next one. Now, the next one, you could think of it as, well, it's a decay because the base is between 0 and 1, or you could think of it like that, which I prefer to do that. Then just ties it in to the other graphs that I already know how to do. So, I'm going to graph y equals 2 to the x first, and then lightly dashed line, and then the negative on the inside with the x of any kind of graph will reflect it across the y-axis. So this is decreasing concave up, and the range is 0 to positive infinity, and the asymptote is y equals 0. So there you go. That's what we're doing for each of these. Okay, next one. So kind of starting all these out the same. So horizontal asymptote, y equals 0, vertical, or y-intercept 0, 1. So e to the x is like that. The 2 makes it twice as tall, 0 to 2. So it makes it steeper. And then the negative flips it upside down. So we're keeping track of that y-intercept. The final answer looks like this. All right, so that is decreasing concave down. Range is negative infinity to 0. You want to start smallest to biggest, so don't do 0 to negative infinity. Asymptote is y equals 0. So there we go. Okay, next one. So yeah, you just crank these out. 0, 1, horizontal asymptote, parent function y equals 0, e to the x, the 3 makes it 3 times taller. The plus 1 moves it all up 1. So I guess I'm kind of running out of room here. So it moves everything up 1. So the horizontal asymptote, the y-intercept. So this is sort of what the graph looks like. Arrows on the ends, darken it in. So this is increasing, concave up. Range is 1 to positive infinity. The asymptote is y equals 1. There you go. Okay, next one. So the parent function is y equals 3 to the x, and then the negative on the inside, I work from the inside out, order of operations. The negative on the inside flips across the y-axis. The negative on the outside flips it upside down. So that's your final graph. And we're keeping track of these. So this is increasing, concave down. Range is negative infinity to 0. Asymptote is y equals 0. Okay, next one. So the next one is horizontal asymptote, y equals 0, 0, 1, parent function. Now the 4 goes 2, 3, 4. So now we're at 0, 4, so that makes it a lot steeper. And then the minus 2 moves everything down 2. So now we're at y equals negative 2, and this is now here at 0, 2. And the graph looks kind of like that. And so the graph is increasing, concave up. Range is negative 2 to positive infinity. Asymptote is y equals negative 2. So, and these are kind of things that we use for any kind of function, all these transformations and shifts and reflections. So this is just good practice for any kind of graph. This should become very quick and easy for you. You gotta just start with parent function. That's the only difference between these and other shapes. So that's y equals 5 to the x. The plus 1 on the inside moves everything to the right 1. So now the point that I'm keeping track is the 1, 1. I don't care that it's not the y-intercept anymore, but I want you to keep track of that one. Then the minus 3 moves everything down 3. And so we have y equals negative 3. And this, oh, sorry, this is the point we should have. So we're at 1, negative 2 now. And so this is your final graph. Arrows on the ends, make it dark. And so it is increasing. It is concave up. The range is negative 3 to positive infinity. And the asymptote is y equals negative 3. So there we go. Okay, last one. Start with the parent function, y equals 0, y-intercept 0, 1, y equals 2 to the x. The negative on the inside flips it across the y-axis. The negative in front on the outside flips it upside down. So now we're at 0, -1, and the plus 1 moves everything up 1. So your horizontal asymptote is y equals 1 now. And so your graph is increasing, concave down, range is -infinity to 1, and the asymptote is y equals 1. So here you go. Got a bunch of graphs in there. So now for problems on the back. So problems on the back are going to solve some exponential equations. And so we want to make the bases the same. And then use rules of exponents to simplify the exponents. So you'd multiply these. 6x minus 2. Now, once you make the bases the same, then you can set the exponents equal to each other. So -2x equals -2. X equals 1. Okay. This would be 7 squared. This would be 7 to the 1/2. So this would be 7 to the 2x equals 7 to the 3/2. Set the exponents equal to each other. Divide both sides by 2. And you get your answer. Set the bases, make the bases the same. 1 is e to the 0. Set the exponents equal to each other. And solve. This is going to be 2 to the 3rd. You might have to change both sides. 2 to the 3rd with x squared, 2 to the 5th. So it's going to be 2 to the 3x squared equals 2 to the 5th. So set the exponents equal to each other. 3x squared equals 5. X squared equals 5/3. Square root of both sides, plus or minus. There are 2 answers here. Now, you could leave it like that. You could break it up. You could rationalize the denominator. Something like that. Okay, next one. Fractions are negative exponents. 2 to the -1. 2 to the 3rd. Rules of exponents. 2 to the -4x equals 2 to the -6x plus 3. Set the exponents equal to each other. And start solving. Add 6x to both sides. Divide both sides by 2. There we go. All right. Number 14. Projected population AG in 20 years at a 2% annual growth rate, and the current population is 1,600. So we're using exponential growth, y equals y naught e to the kt. This is our y naught. This is our k. This is our t. So we're just going to plug these things in. 1,600 e to the 0.02 times 20 years. So the exact answer is 16,000 e to the 0.4. On your calculator, that'd be 23,869.195 people, something like that. 15, find the annual growth rate. So we're trying to find k. The town that's doubled in 8 years, so it's doubling time. So we're using y equals y naught e to the kt. We don't know the initial population or the current population, but we know that it's doubled from whatever it was. The time is 8 years, so now if we divide both sides by initial population, it drops out. And we take the natural log of both sides, and so then we get 8k equals natural log of 2. We're going to divide both sides by 8. So the exact answer is k equals natural log of 2 over 8. As a decimal, it is 0.0866433. As a percent, which is common, it's 8.664%. On your calculator. 16, 1986 new car averaged 9,000, 1991 averaged 12,000. Use an exponential model to predict the cost of a new car in 2015. So we need initial amount, which could be either of these. We also need the k value, and then time will just depend on if we use 86 or 91 as our initial value. So we definitely need y equals y naught e to the kt, and we can use the price of 12,000 and use 9,000 as the initial. And then k, the time passed from 86 to 91 is 5 years. So we need two known points to find the k value. So then we're going to divide both sides by 9,000, start solving. 4/3. Take the natural log of both sides. Divide both sides by 5. So your k value is exactly natural log of 4/3 over 5, which you could use, or you could use it as a decimal, 0.05753644145. You want to carry extra decimals if you're going to use that decimal to calculate something else. So then we could say, okay, well, we could either start at 9,000 and use our k value. Now, 9,000 would be 86, so there'd be 14, that'd be 29 years. So you can use that. Or you could use 12,091. Same k value, but the time is going to be 24 instead. Now, if you do this, we get 47,740.524. So either way should give you that. Rule of 70, we talked about it in the notes, so you guys can use that. It's a way of estimating doubling time. By dividing 70 by the interest rate or growth rate as a percent. And it equals the number of whatever units of time, which is often years, but doesn't have to be, required for doubling. So doubling time, I mean, you can show how this is figured out. So then we take the natural log of both sides. We can bring that in front. Natural log of e is 1. And then we divide both sides by k. And so k equals natural log of 2 over k. which is about 70. It's like 0.7. It's actually, I think, 6.9, whatever, over K as a percent. So there you go. Okay.